9. Ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
50 years ago, we set foot on the moon for the first time.
It's one small step for man, one giant leap for mankind.
We bounced around in the 1/6 Earth gravity, took some pictures, gathered rock samples, and then we came home.
Port stage, engine arm ascent, proceed. Down, beautiful. 26, 36 feet per second up. Very smooth.
We went back a handful of times, never staying longer than a few days. We got more adventurous, driving a rover across the dusty, cratered landscape.
We set up science experiments, hit some golf balls, and collected lots and lots and lots more rocks.
Not many small walnut-sized fragments in here, Bob. Gotten about 7 or 8. Okay, I copy that. Gene, you got a bag? Yes, sir, right here. How you doing? My hands are getting tired. Bag 501.
Reaching our closest celestial neighbor was one of the defining achievements of human history. But dreams of staying there would have to wait. There was no place for us on the inhospitable lunar surface.
So we left.
And as we leave the moon in Taurus Littoral, we leave as we came, and God willing, as we shall return, with peace and in hope for all mankind. Godspeed the crew of Apollo 17.
Have a podcast about energy.
The jewels that these national labs are.
In terms of science and scientific capabilities.
Big dreams can happen.
Keeping our nation safe.
Clean energy is the way of the future. It's America's economic engine.
It's science.
For the people.
This is Direct Current.
You're listening to Direct Current. I'm Matt Dozier.
And I'm Court Creer.
It's been 46 years since humans last stood on the moon. Today, the U.S. is looking to go back for longer this time, possibly even for good. And from there, on to more distant destinations. Here's NASA Administrator Jim Bridenstine speaking at a press conference about the Moon to Mars mission earlier this year.
The moon is the proving ground. Mars is the horizon goal. And it requires an all-of-the-above approach.
We're going to need some new technologies if we're going to make this work. And near the top of this new mission checklist is a power source that's up to the task of long-term human space travel.
Lee Mason is the Deputy Chief Engineer for NASA's Space Technology Mission Directorate. Lee has some experience with what works and what doesn't when it comes to space power.
Weight is a major premium, and power systems can't take up too much of it, or we don't have enough for our payload and our instruments. Beyond that, we're looking for power sources that can operate in very extreme environments. So, on the moon, the temperature gets as low as 100 degrees Kelvin during the lunar night and as high as 370 Kelvin during the lunar day.
Side note, in Fahrenheit, we're talking minus 280 degrees to over 200 degrees.
And so those big temperature swings can wreak havoc on power sources. So you need a power supply that is resilient to those kind of conditions.
Lee's at the helm of the space agency's search for an energy source that's small and light enough to fit on a rocket, tough enough to endure the rigors of space travel, and powerful enough to keep astronauts alive for months or even years.
All right, so let's take a quick look at our options. Gasoline or other combustion-powered generators won't work because of limited fuel storage. Plus, they need oxygen to run. Wind turbines are out for obvious reasons.
Solar power is a natural fit for space travel, with a few big exceptions. On the moon, you get roughly 2 weeks of sunshine, followed by 2 weeks of darkness. So any solar panels would have to be paired with some serious battery storage. And Mars, which is NASA's next destination, has its own challenges.
Mars not only has dust, but it has major dust storms. And in fact, back in June of 2018, the rovers that we have on the surface of Mars were subjected to a 2 or 3 month long major, planet-wide dust storm. You can imagine if you had to rely on solar power to keep crew alive on the surface of Mars during that dust storm, we would be in big trouble because the dust would completely obfuscate the potential for using those solar arrays.
For Lee, there's one energy solution that stands out from the rest.
I spent most of my 30-plus year career working in space nuclear power systems, so I have a long background in it. The thing about NASA missions is, you do the ones you can do easily first, and then as you check those off, the missions become harder and harder. And it was pretty obvious to me that in order to accomplish some of the harder ones, we were going to need a new power source like nuclear reactors.
That's right, nuclear reactors. We did a whole episode on nuclear energy recently, so if you want to learn more about how it works here on Earth, go give that a listen. But we're talking about space here, where the rules are completely different.
Nuclear has actually provided the power for a bunch of space missions over the years in the form of radioisotope thermoelectric generators, or RTGs. They're essentially batteries that use the radioactive element plutonium to produce heat and electricity for spacecraft like Voyager 1 and 2, Cassini, New Horizons, and the Mars rovers.
Even the Apollo moon landings used a rudimentary nuclear heat source to keep their experiments from freezing on the lunar surface.
We were very comfortable with those, and they worked great. They did a lot of fantastic missions for us, but they were limited in power level to a couple hundred watts or so.
A few hundred watts is plenty for a mission like New Horizons, which only needed a modest supply of electricity for instruments on its historic flyby of Pluto. But humans need a lot more power to survive in space than a robotic rover or space probe. We need warmth, breathable air, and enough fuel to eventually return to Earth.
Nuclear power on the moon makes a great deal of sense because we could use it to power plants that would extract water from the permanently shadowed regions in craters at the South Pole. And if we could do that, if we could extract water from this ice, we could make oxygen to breathe and fuel to power our rockets.
All of that is energy-intensive work. So if we're going to undertake new challenges involving humans, like sustaining a permanent presence on the moon or landing people on Mars for the first time, we're going to need more juice than our trusty nuclear batteries can provide.
So we were looking at, could we size a space reactor, a fission reactor, small enough to compete with the RTGs? And that's how that activity kind of got started. And as a result, ultimately, we developed the Kilopower concept.
Kilopower is the name of NASA's effort to create a miniature nuclear reactor, just a fraction of the size of the ones used in nuclear power plants, that could replace RTGs as the go-to power source for space exploration missions. The goal of NASA's Kilopower project is to generate up to 10 kilowatts of electricity, more than 100 times what an RTG can put out.
We should say 10 kilowatts isn't all that much power. It's about what you get from a portable gas generator. And it's a minuscule amount of energy for a nuclear power plant, which typically operate on the scale of thousands of kilowatts. But when you're talking about a decades-long venture into deep space, it's a really significant undertaking.
1 to 10 kilowatts is a tremendous amount of power for systems that can provide the continuous power in the extreme environments that nuclear offers.
Okay, so how is Kilopower going to manage that?
First, let's talk about how RTGs work real quick. Plutonium-238 is naturally radioactive, so it generates heat all by itself. Stick a chunk of plutonium in an RTG, put it on a spacecraft, and you can use the massive temperature difference between it and the cold vacuum of space to generate electricity.
One thing that doesn't happen in an RTG is nuclear fission. That's different. Fission is the powerful chain reaction of splitting atoms that lets commercial nuclear reactors generate enormous amounts of energy.
And nuclear fission is what the Kilopower team plans to harness for their space reactor, just on a much smaller scale. Instead of plutonium, reactors use uranium-235, which isn't anywhere near as radioactive as plutonium-238.
It all starts with uranium fuel, and the process of fission takes place where a neutron encounters an uranium atom, and it causes the atom to break in two. And as it does that, it releases energy, basically via E equals MC squared.
That's Dave Poston.
I guess my title is the Chief Reactor Designer at Los Alamos.
You say you guess. You don't sound too...
Well, no, it is Chief Reactor Designer. Well, I guess it's because I don't know if I really like that title, but that's what they gave me. So.
Like it or not, Dave is the head designer for nuclear reactor projects at the Los Alamos National Laboratory in New Mexico, where he has been partnering with NASA on the Kilopower project since 2012.
In addition to the uranium fuel source, there are two other key components: the heat pipes and the Stirling engines. When the core starts getting really hot through nuclear fission, that heat gets transmitted into the heat pipes.
Inside the heat pipe is a liquid metal, sodium. When the heat enters the heat pipe, it boils the sodium, travels along the heat pipe, and condenses, kind of like how heat will condense on your stove top. So if you ever put a lid on top of boiling water, that lid gets real hot real fast. And it's the same kind of thing. The sodium goes up and condenses up at the Stirling engine and transfers the heat there. And then the heat causes a piston to move back and forth inside the engine, which then moves a magnet inside a coil to make electrical current.
Pretty simple, right? The action of the sodium boiling and turning back into liquid in the heat pipes over and over again continuously moves heat away from the uranium core to the Stirling engines, which are basically simple piston-driven generators.
The heat pipe technology is one part of what makes the Kilopower design so compelling. It's self-contained, efficient, and has almost no moving parts, making it reliable over long periods of operation.
Really what's cool about Kilopower is it's designed to be simple in how it operates. The way I like to say it is the reactor is like a thermostat. Due to its nuclear characteristics, it has a strong natural desire to remain at its set point temperature. So let's say that's 800 degrees Celsius. And so it's going to stay at that temperature and produce whatever power is taken from that reactor. And so if the Stirling engines say, I want more power, they start to draw more power at the heat pipes, the reactor is going to initially cool down and say, wait, I want to get back to 800 C, and it's going to produce more power. And so we call that a load-following system. The reactor will put out whatever power is demanded from it because it really wants to stay at its temperature. And if you shut off all the Stirling engines and there's no heat being removed, the reactor power will go to zero.
In this case, simplicity equals safety. The thermostat Dave talked about is baked into the design of the reactor. There are no control rods that need to be inserted or removed to regulate the temperature, or water needed to cool the reactor core. The hotter it gets above a certain point, the more it puts the brakes on the nuclear reaction. It's just basic physics doing all the work.
Yeah, and basically safety is tantamount to reliability. If tantamount's the right word, I don't know. But you know, if there's a human being counting on the reactor, the most important thing is reliable because they need the power. They're going to be in trouble without the power. So we put in a lot of redundancy. In the case of Stirling engines, say we have 8 Stirling engines, we design it so that a couple can fail and we still produce full power, and then if a couple more fail, we still produce some power so that they're not going to be at the point real quickly where they don't have any power. And the reactor is so simple that it's basically just a couple of chunks of metal. So that is almost fail-safe. There are ways heat pipes can fail, but it's the same thing. There's several heat pipes just like there's several Stirlings. So we put in a lot of redundancy to make sure we're always producing power.
In a recent round of tests, the Kilopower team subjected the reactor to all kinds of worst-case scenarios. Nothing they did caused more than a hiccup.
We turned off all the heat removal, and it heated up some. But then, due to its nature, it stopped producing power because it wanted to try to get back to its thermostat temperature. And so it basically turned off the power and started cooling back off.
That test happened in March 2018 at the Nevada National Security Site, managed by our National Nuclear Security Administration. And it was actually a pretty big deal. They ran the reactor at full power for more than 24 hours straight, and it worked perfectly, showing that it could really be the answer NASA is looking for.
The experiment was called the Kilopower Reactor Using Stirling Technology Test, Krusty for short. If you're a regular listener to this show, you may recall that we had a Simpsons-heavy theme in our nuclear energy episode. Well, guess what? It's back.
We can't seem to escape it.
Basically, all engineering groups at Los Alamos kind of a history of giving nicknames to projects. One of the first designs I ever did, I called it Homer, for 3 reasons. One, because of Homer Simpson, but the other is because of the Iliad and the Odyssey Homer. And the other was it's a home run. So you have like all sorts of positive connotations. So then like another thing came up that was similar that had a good acronym named Marge. And so then all of a sudden I became the Simpsons guy. And I am a Simpsons fan. But so then after that, it was basically I tried to come up with acronyms that fit Simpsons characters.
Most people got a kick out of the names. Most people.
There was some resistance, which is really funny because Krusty, I don't know if you know who Krusty is, but he's kind of a drunk clown. And so we had several people saying, well, we can't name a reactor after a drunk clown. but we had already gotten it like officially named in some paperwork, so we decided to keep it.
But Dave and the Los Alamos team didn't go from Homer to Krusty overnight. Rewind to 2012 when Dave was actually feeling pretty down about the prospects for his reactor designs ever making it into space at all.
Basically, what happened to start this project was in 2012, we just sat down and say, what is something we could actually do really quick and really fast to prove to NASA, let alone prove to ourselves, that we can still design, build, and test a nuclear reactor. Because DOE, outside of naval reactors, hasn't built and operated a new nuclear reactor since the DOE was formed, which is really kind of a stark reality that people always talk about.
What came out of that soul searching was a simple demonstration taking the basic reactor concept, uranium core, heat pipes, Stirling engines, and putting it in action as cheaply and as quickly as possible. And of course, it sported the trademark Dave Poston acronym.
So that was the DUFF experiment, DUFF, demonstration using flat top fissions. We basically, with a little bit of internal money, I think we spent like $500K, went there and actually used a heat pipe in an existing system they had there that operated as a reactor coupled to some Stirling engines and a light panel. That was it, basically.
And NASA liked it.
We said, okay, we're going to do this little experiment, and by doing that, we're going to prove to you that building a small reactor and testing it is not completely crazy.
Pat McClure is the Kilopower project lead at Los Alamos National Lab. He's been at the lab about as long as Dave Poston, around 25 years, and the two of them have seen plenty of reactor projects come and go, without much success.
You know, in the past, we had spent really long time frames, like in some cases decades, and spent a lot of money and hadn't really made a lot of progress. And so we had sort of envisioned Kilopower as sort of being a very simple reactor. Low power, very simple. You know, let's get nuclear power back into space.
DUFF provided some thrust in the direction of the problem, and it gave their team the confidence to take the Kilopower reactor concept and run with it. But first, they needed buy-in and funding.
So we put that together as a strategy, and then we did what I called the roadshow. We went to try to convince Nevada, NASA, and NNSA, our own laboratory, and others that this was doable.
Los Alamos signed on. So did NASA. The Nevada National Security Site agreed to provide the test location, and Y-12 National Security Complex in Tennessee would provide the uranium fuel. And vitally, the National Nuclear Security Administration stepped in to help fund the project and keep things moving smoothly.
The design of Krusty experiment is very simplistic. That's part of its beauty, is how simple it is. It's just a big chunk of uranium with a neutron reflector that goes around it that drives it critical, and a control rod at the center. Organizationally, though, we had a lot of moving parts, and my role was to keep those moving parts in sync.
Dr. Angela Chambers is the Department of Energy's Nuclear Criticality Safety Program Manager, which means she oversees several sites that do nuclear experiments involving criticality, aka fission.
As we established earlier, that includes Kilopower. And she's quick to point out that there was more to the Krusty experiment than we've discussed so far.
So Krusty kind of had two roles. There was a NASA role to produce power for deep space missions or manned missions to Mars or the Moon. And then there's the DOE part of it, which was the criticality experiment for us, where we got nuclear data and we've got a critical experiment benchmark that we'll use for NNSA purposes for basic nuclear data.
So in 2018, the stage was set for Krusty to perform. And unlike its cartoon namesake, its delivery was flawless.
And they actually took the Krusty reactor core critical more than 80 times during the 14 weeks of experiments, with the final critical run being a 28-hour continuous run.
That 28-hour stretch was a new record for a fission reactor test at the Nevada site. Not only did it work like a dream, they gathered all the nuclear safety data they'd hoped for.
And we successfully turned the Stirling engines to generate electricity as we intended. So that was very successful.
So successful, in fact, that the team won a presidential award for their work on the design and successful testing of the Kilopower reactor.
Yeah, it's the inaugural Gears of Government Awards, which I had not realized that when we first won the award, that this was the first year for it. So, yes, very pleased, very happy. It's a true reflection of all the work that went into it at all the different sites and all of the people. I mean, there are hundreds of people that were part of the Krusty project at one point or another.
Awards aside, this was a big milestone for nuclear reactor design and testing at the Department of Energy and our national labs, especially for Los Alamos, which has invested a lot in this work over the years. Not just money, but time, energy, and faith in the homegrown tech that makes it all work.
Now, there's a reason we pick heat pipes. They were invented at Los Alamos in '63. Quite frankly, they're used everywhere. Do you have a laptop?
Yeah.
It's got heat pipes in it, dude. They're water heat pipes, but almost every single laptop has heat pipes. It's nice for us because it's a really nice passive way to get heat out of the core to our power conversion. We don't have to worry about things melting or freezing like a lot of applications. We don't have to worry about pumps. It works out great because we're such a very tiny reactor.
So heat pipes have found their way into all kinds of stuff over the decades, except, ironically, what the original inventors intended, until now.
The initial group of guys actually envisioned it as a way to cool reactors. That was almost the main purpose they designed the things for.
Most of the original creators of this technology are no longer with us. George Erickson, the man who built one of the very first heat pipe prototypes one afternoon at Los Alamos in 1963, actually just passed away earlier this year. But their pioneering work lives on in projects like Kilopower.
Dave Poston has done plenty of his own dreaming about space travel, and not just during the 25 years he's been at Los Alamos.
I read a lot of science fiction, as a kid in junior high and high school, and definitely got the bug for space exploration early, and I was in elementary school during Apollo, so that's the normal story for a lot of people, like when we're landing people on the moon. That's probably where I got most of my excitement.
NASA is still considering options for Artemis, its upcoming mission to send astronauts to the moon's south pole by 2024. Kilopower doesn't yet have a confirmed seat on the rocket, so to speak. And there's still a very real chance it could get passed over in favor of another concept.
That leaves Dave, Pat, Angela, and the rest of the team feeling proud of the work that they've done to prove their little nuclear reactor's worth, and cautiously optimistic about its place in space.
I feel great about it, but it's got to lead to the next step, or, it won't be that great. I guess it'll always be great that we showed we could operate this reactor, understood all the physics, and the technology works, but it's kind of like the guys that maybe just got to the playoffs, it's like, so you're happy, but maybe reserve your celebration until you win the championship, kind of thing.
Future space missions are only going to take us greater distances from Earth for longer stretches of time. And the further we travel, and the longer we stay away, the more appealing a small nuclear reactor's reliability and longevity becomes.
That's important because it means higher power demands, longer life power sources, and trying to live off the land, mining ice from craters and oxygen from regolith. And these things are going to demand new power sources like Kilopower. And so I think the opportunity is definitely here. It's probably as good as it ever has been in terms of mission pull for small reactors. So I'm pretty confident we're going to move forward and do something meaningful.
That's our episode. A kiloton of thanks to our guests Lee Mason, Dave Poston, Pat McClure, and Angela Chambers for their help and expertise on this story.
The audio of Apollo 17 astronaut Gene Cernan's final words on the moon was courtesy of Apollo17.org, an extremely cool interactive mission timeline developed by Ben Feist.
As always, if you've got a question or want to leave us some feedback, email us at directcurrent@hq.doe.gov or tweet at Energy.
And if you're enjoying the show, share it with a friend or leave us a review on iTunes. We read them and we listen.
Direct Current is produced by Matt Dozier, Paul Lester, and me, Court Creer. I also create original artwork for every episode, and you can find that on our website.
We're a production of the U.S. Department of Energy and published from our nation's capital in Washington, D.C.
Thanks for listening.